This video is going to be a review with some of my insights and feedback to you guys about particle motion and diffusion that go along with the simulation handout. I'm going to make this video over the first two in-class guided activities. So follow along on your worksheet, write down your interpretation along with my feedback and how you should be imagining the relationship between particle motion and diffusion. The first in-class guided activity simply wants you guys to imagine diffusion. So if you have a cluster of dye particles, it's interesting that eventually, like we modeled in class with the blue dye demo, the dye particles end up making their way evenly throughout the whole sample. But we want you guys to start looking at individual or group particle behavior. On question 1, it asks, do all the particles move the same speed? At first glance, some students say the particles are all moving the same speed. But if you carefully look at the particles, especially before and after collisions, particles are going at a variety of speeds. Some are slower than others, and that changes after particle collisions. So you should put no, they don't all move the same speed. And that's how you need to imagine particle motion, especially in these liquids and gases for diffusion. On number 2, I want you to observe two particles colliding. What happens to the speeds of the particles after they collide with each other? I'm going to use slow motion on this to kind of show the before and after. So focus on one particle. If you watch these particles around my cursor, what do you notice happens with the speed before and after collisions? You guys should have some sort of note about how one increases speed and the other decreases speed. I think for the most part, the faster particle, after it collides with a slower particle, the faster one is the one that decreases speed, and the slower particle increases speed in general. I want you guys to also think about in what ways can energy ideas account for or explain why the speed changes. Changes have been a major theme this year, and you guys should be thinking about energy transfers being associated with changes. And if you have changes in speed, you need to be thinking about how speed is related to EK, or kinetic energy. There's more to come on energy transfers in the next week or so. Question 3 talks about how do the particles behave after one collision, but before the next one. So focus on the motion of one of the particles. You should observe that a particle goes in a straight line or a straight path after a collision and before another one. And it appears that they go at a pretty constant speed. So individual particles are at a constant speed on a straight path. However, if you trace a random particle, let's observe the motion. So on number 4, how would you describe the path of the highlighted particle? You guys should make a note that the pathway is very random. Why do you suppose it's random and not in a straight line? Students should be thinking about how collisions are manipulating the path that the particle would normally want to take without any interruptions. On number 5, at least what two things must be occurring for dye to spread out and diffuse through the water? You should be thinking about The particles need to be in motion. There needs to be collision for random spreading. And you should probably also note space between particles is a major idea. Think about if there's no space between the particles for the dye to pass through or to ricochet through. I don't think we'd have the phenomenon of diffusion at this point. So make sure you have notes down, your own responses on questions 1 through 5 on the in-class guided activity 1. I'm going to transition to in-class activity 2. This activity wants you to compare the diffusion compared to temperature and think about the relationship between the two. So we're going to manipulate the temperature on the next simulation, and we're going to collect information about how fast it takes for diffusion to occur. We're going to write down the time it takes for medium temperature to diffuse against the green particles to reach the gas sensor. You may want to run this trial a couple times. So for medium temperature versus high temperature, what do you think the outcome is going to be? Do you suppose high temperature will be faster, slower, or the same diffusion rate as at medium temperature? Remember, it seems like there's a connection between particle speed and temperature at this point, noted from the dye demo in class and these simulations. On medium temperature, it took about 8.6 seconds. I'm going to switch it and reset it to high temperature. Compared to 8.6 seconds, high temperature, is it going to be faster or slower or the same diffusion rate? Note that the time is 4.5 seconds. Make sure you guys run this on your own or write down my information from my demos. So number 2 asks, write a claim about the relationship between diffusion and temperature. So what would you write for a claim about diffusion versus temperature? You should be writing something along the lines of, as temperature increases, the rate of diffusion increases. You could also write the opposite of that. As temperature decreases, diffusion rate decreases. Make sure you make your own note of that. On question 3, let's reconnect particle motion and temperature connections here. What's the connection between particle speed and temperature based on these simulations? You should have something written down that as temperature increases, particle speed increases. And that was inferred even in class from the dye and water demo from cold water versus hot water. The hot water dye spread and diffused throughout evenly, much quicker than the cold water. Make sure you guys have your notes updated for in-class activity 1 and in-class activity guided activity 2. I'm going to make a video for the other extensions. Make sure you follow along with them. Think about particle behavior, the manipulation of diffusion through temperature and mass, and complete those ones as well.